Today we're going to start with the Ospf, which is Open Short Spell First. As I've told you always, first of all, I used to go through the basic overview, the introduction part, the theoretical concepts, because theoretical concepts must be clear in order to go ahead and start implementing or configuring the topology with the help of this protocol. OSPF, like we did using EIGRP or RIP version 1 and 2. So let's go ahead and I'm going to tell you about it now. So we can say it is a link state routing protocol, right? I told you before there are two types of protocols: distance vector and link state routing protocol. So this OSPF is a link state routing protocol because BACAUSC, because it is an open, it's not Cisco's proprietary protocol, it's an open standard, so you can implement it in Cisco as well as any other routing, or you can say in any other routing device, whether here that device is from Cisco or from Juniper or from Amazon or from different vendors in this world. So you can implement it on any particular device. All right, so it is implemented by a variety. That's why most of the vendors use OSPF instead of EIGRP, because EIGRP we have to have the Cisco in this EIGRP, we have to have the Cisco routers, then only we can. So every router in the network should be should be first of all from the Cisco, then only we can use EIGRP. But here, if you use OSPF, whether you have the Cisco router, whether you have another router in the same network from a different company like Juniper, from Amazon, from Dell, from IBM, so it doesn't matter. It's an open standard and it can be implemented on any particular router. That's the most important thing in this. But still, there are some problems. There are some, you can say, drawbacks of OSPF also, which I'm going to tell you later on. So just go through the basic overview. So it's implemented by a variety of network vendors, VNDRS vendors. So OSPF, another point is OSPF will run on most routers that does not necessarily NECESSARILY have to be Cisco routers, unlike EIGRP, which can be run or which can be configured only on Cisco. That's the main advantage of OSPF Cisco routers. So this is the first point. It's a link state routing protocol because it's an open standard and it's implemented by a variety of network vendors like IBM, any network vendor that we do have, they have this because it gives you the simplicity. If there are some you can say less, or you can say some some routers which are of less price, we can use them also. But if you have EIGRP, so whatever the price you have for Cisco routers, you have to buy them, and then only you have to implement them in the network, and then only you can go ahead and use this EIGRP. But OSPF is open for you, whatever the routers you have, whether you want to go for cheap routers or costlier routers, you can go ahead and use OSPF for that. So that's the advantage that OSPF is having. So after that, the most common features of, apart from this, there are most common features of OSPF. First of all, again, same like as EIGRP, it's a classless routing protocol. What do you mean by classless? So it can be used for subnetting also. So only classful IP addresses is not the dream that you can do here. You can go beneath it and you can just subnet the particular network ID and go for more than one subnet, and it supports variables. At the same time, if it's going to support classless routing protocol, and obviously it should also support VLSM, which is basically variable length subnet mask, CIDR. It supports it. Then it supports manual summarization, but manual route summarization. But I will tell you later on where it's not for every router. Like, this is the drawback, because it supports manual route summarization, and even it supports equal cost, but it supports only equal cost load balancing. But there are conditions balancing. So it supports all these features, and it's going to send incremental updates are supported. So it's going to send incremental updates. So we can say that, oh my God, updates. Updates are supported. SUPPORTD. Wait a sec, let me take the attendance here. Only you or the people who are present. Okay, us. We don't need anything else. Let me take the full screenshot. That's it. Okay, and also uses only one parameter as the metric, which is cost. So metric, which is the interface cost, the cost of interface. So that's the parameter which it uses. So the metric of OSPF is cost. All right. So you need to remember these are the things, which you will be asked. What's the metric of RIP now? It's hop count. What's the metric of EIGRP? It's bandwidth and delay. What's the metric of OSPF? It's cost. All right.
Yeah.
The AD value after that. So administrative distance, AD. I'm going to write it in short. So administrative distance value of OSPF is by default. Yep. How much it is?
110.
Yeah, 110. All right. And here it uses multicast address 224. It uses two multicast addresses. Why? I'm going to tell you later on. It uses 224.0.0.5 and 224.0.0.6 for routing. So for you're being, getting the information about each particular routing protocol used only one particular multicast address to send the routing updates. And here also it should use one, then Y2, because it has to send, every router will share the information. But we have very important thing here, which I'm going to discuss to you later on. So these are the important things that are, you can say, the latest features are the features that we do have in OSPF. Okay, clear? Now about the concept, how the OSPF is going to work. So first of all, routers running OSPF. So those routers who are having the running configuration of OSPF have to establish, or can establish, or how they can establish the neighbor relationship. So they can establish the neighbor relationship before exchanging So this is just what is the mechanism. The mechanism is same. So every router who is running or who is having the configuration of OSPF have to or has to establish neighbor relationship before exchanging the routing information. So this point is same as EIGRP, because in EIGRP also, before a router sends the routing information to another router, first of all, they need to create the neighbor relationships, right? So how they created the neighbor relationships? Because of the same autonomous number. But here is something different. We have something different here. So because OSPF is a link state routing protocol, neighbors cannot exchange routing tables. You understand? So as I've told you what happens in distance vector protocols and link state. So instead they exchange information about network. The entire network topology will be shared. That's why this is the drawback of this link state vector, link state routing or link state vector routing protocols, because they share the entire network topology to the neighboring routers. That means there will be three tables like neighbor table, topology table, and routing table. In EIGRP, it's going to share only the routing table, not the topology, not the network topology. The entire three tables will be shared every time in OSPF. So which in turn increases the bandwidth of the network. You understanding?
Yes.
So in here, exchange routers exchange information about network topology. In EIGRP topology, it was exchanging, the routers were exchanging the routing tables, only routing tables, to just decrease the bandwidth. But here, routers exchange information about routing topology. So each OSPF router then runs SFP, shortest path first. This is the algorithm it's using. Algorithm runs SFP, which is S stands for shortest first path, or shortest path first. SFP algorithm runs SFP to calculate the metric, the best routes, and adds those to the routing table. So then when entire network topology will be shared to another router, it's going to just calculate. It's going to use the algorithm, which is SFP algorithm, to calculate the best routes from that particular network topology. It's going to calculate automatically the best routes, and then those best routes will be stored inside the routing table. You understanding? So this is the concept. For example, we are going to draw a topology here. I have one network here, or one router here. This is my own router. So what happens? So this is another, this is another, this is another, and this is another. They are all linked together. So this is my router R1, and this is R2, and these are routers. So every router shares the information, and when they share the information, suppose that this is, I'm taking example of this router. So I have directly connected subnets like 2, so they are directly connected, and now I need the information of all these networks. When they share update after establishing a neighbor relationship, so SPF is being implemented at that time when, for example, it's having 5 routes, okay? So it's having routes, it's having routes to reach in this network. These are also having. So when all these will share the routing information to this this router, so what will happen? It will just take those all and just calculate. Automatically, it will calculate using this SPF algorithm the best routes, and those best routes will be added in the routing table. Just, it's going to match. Using that algorithm, it will match what's the best route to reach, what's the fastest way to route. Suppose that here is one more router. So it will not add this route, it will add this route in the routing table, because here is the hop count and it's more than, so interface, like even if you take 10 10 10, that means 30 is the cost. From this way it's only 1 10, it's 4 30 40, but in this way it's only 30, it's 10 20 30 and 40, and it will just take this route and put it in the routing table. Got it?
Yes.
So why it's doing that, why it takes the routing updates of all, and then at the same time it calculates the best route and puts that in the routing table. It cannot add the entire routing topology in the routing table because there are chances. So because each router knows the entire topology in this particular network, while you have OSPF configured, in this type of network, every router knows the entire topology of a network. What's the entire, because you are sharing the topology. You're understanding? You're sharing all these things, like we have neighbor table, topology table. So you're sharing. So every router knows that. So it's going to increase the chances of a routing loop to occur. So it will just not increase the chances. So there are less chances. The chances for routing loop to occur is minimal because every router knows the network topology, not the routing table. So there are less chances, not increase. It's in RIP. So in link state routing protocols, we are having less chances of loops to occur, because the main factor is, if there is a question why there are chances, why there are minimal or less chances of routing loops to occur in, in OSPF like protocol, you should say simply that basically every router knows the entire network topology. That's why every particular router is having the information about each route. So there are less chances of routing loops to occur. That's the main important thing you have to tell. Clear with this?
Yeah.
Okay, so now each OSPF router stores routing and topology table information in 3 tables, same as EIGRP. So first one is, what is that? NEIGHBOR, neighbor table. What do you mean by neighbor table, and what's going to store? It's going to store the information about OSPF neighbors, right?
Neighbors.
Then topology.
Yes.
Topology table, what's it? Is going to store the topology structure of the network. And then routing table, which is going to store the best routes, stores the best routes. So these are the 3 tables that will be created in each OSPF router within a network. So neighbor table is going to store the information of neighboring routers. Topology table will just store all the, what happened here? Why I deleted this thing? All right. Now, talking about OSPF neighbors, how neighbor relationship is being established in OSPF. So OSPF routers need to establish, as I've told you, they need to establish a neighbor, N-I-E-G-H-B-O-R, neighbor relationship before they exchange the routing information. Before exchanging routing information or routing updates. You know it. So because every router need to do that. So OSPF, N-E-I-G-H-B-O-R, neighbors are dynamically discovered by sending hello packets like EIGRP out to its packets out to each OSPF enabled interface on a router. So this is how neighbor relationships will be formed. So basically, OSPF sends the hello packets, same like as EIGRP, it sends the hello packets. Now, only the difference is how the neighbor relationship will be formed between the two routers or between three routers or between all the routers in the network. So hello packets are sent to the multicast IP address of 224.0.0.5. So those all hello packets, when you have to establish or create a neighbor relationship with your neighboring router, so the hello packets are sent with the help of an IP address, the multicast IP address, which is in front of you, which is 224.0.0.5. All right. So, for example, again, I'm going to take an example. Suppose that you have, do we have stickers here of routers? Fruit, bowls, everything. Emojis, math symbol. Not an issue, we'll draw it. Suppose there is one router and here is another router. This is router R1 and this is router R2. Okay. And they are configured and OSPF is configured. So routers R1 and R2 are directly connected, right? After OSPF is enabled, both routers send hello packets to each other. When you configure OSPF to them, in order to create the neighbor relationship, in order to establish a neighbor relationship, both the routers will send out hello packets from their interfaces to establish a neighbor relationship. So we can verify that neighbor relationship using the show we can verify the neighbor relationship by the command show in the same way like we did. Instead of EIGRP, we're going to use OSPF neighbor, NEIGHBOR. So this is the way how they are going to create the neighbor relationship. When OSPF is configured in both interfaces, so they will send out the packets, the hello packets, to create or to establish a neighbor relationship. All right. So in this example, wait a sec. The fields in the hello packets must be the same on both the routers in order for routers, or in order to establish a neighbor relationship, in order to establish a relationship. So first packet subnet should be same subnet. Second is, there is, instead of autonomous number here, we have area ID. You understand? Then hello and dead intervals, interval times, they should be same. And also authentication. Authentication has to be same. And then at the fifth area, stub flag, which I'm going to tell you later on. Stub flag, and then MTU. So these are the 6 different things. Instead of your autonomous number in EIGRP here, they are going to create mostly the neighbor relationship based on this area ID. So these are the 6 fields that will be advertised from router R1 towards R2, and R2 will also advertise. And all these 6 packets, or 6 particular, you can say fields in a packet should be same. Then only a neighbor relationship will be made. You understanding? So this is area ID. Clear?
Yes.
So now the time intervals. So by default, Ospf sends hello packets after every 10 seconds on an Ethernet network, in a local area network, you can say, or where there is Ethernet network. That's called as hello interval. A dead timer is 4 times the value of the hello interval, or hello packet. So that means 40 seconds is the dead timer of, the hello intervals which are being sent. For example, are you awake? Are you awake? These are hello packets we are just sending, as I've told you, to check whether the router is just turned on, or it's working, it's processing. So we send after every 10 seconds. If you have OSPF, it sends the information, it sends the hello packets, creates the neighbor relationship. So if there is any problem in the network, then I told you it's going to wait. It's going to wait up to 40 seconds, and then the dead timer will start. So that's what I have wrote here. So a dead timer, it's not timers, its timer is 4 times the value of hello interval. Okay. So if a router, or if routers on the Ethernet network does not receive at least one hello packet from an OSPF neighbor for 40 seconds, the router declares the neighbor to be down. So 40 seconds is the dead timer for OSPF. After that, router declares that neighbor or neighboring router to be down. You understand? Are you getting?
Yep.
Yes.
Yes.
So these are the things you need to remember, these seconds, time, and so for EIGRP, it was sending just for 5 minutes, and then 3 times was the dead timer. That means about 15 seconds. Here, dead timer is 40 seconds. After every 10 seconds, it sends the hello packets to make sure that the router is, is awake, or it's just still working. It's turned on. It's not down. So after 40 seconds, suppose that the network is down, the router waits, the neighboring router waits up to 40 seconds, and after that, it's going to start that. It's making sure that it declares that the neighbor is down. Okay? Now, OSPF, There are a lot of things about it which you need to remember. That's why I'm just writing all those things. Now, the neighbor status. What are the states of neighbors and how they establish the relationships? So before establishing a neighbor relationship, OSPF routers need to go through several state changes. These state changes are, so when you establish a neighbor relationship, when you send the hello packet, how that hello packet is basically working, what's the process of that? So there are different status. So you can say neighbor status, NEIGHBOR, neighbor states. First status is init, INIT, init state. What do you mean by init state? When you send a hello packet, a router has received when, for example, this is a router and R1 sent a hello packet to R2. Now it received it. R2 received the hello packet. That means a router has sent a hello message from the other OSPF router. That means now it's in the init state. When one router like R1 will send a packet, a hello packet to the other neighboring router, so that means it is in init state. Are you understanding? So that is in its state. Second is two-way state. What do you mean by two-way state? Now, two-way state is the neighbor has received the hello. For example, R1 has sent the hello packet. Now, R2 has received the hello message and replied with a hello message of his own. You understand? So when R1 in init state, it is just message has been sent, a hello packet has been sent, that's init state. R2 two-way is when R2 will receive and it will just send the message, hello message back to R1. That is two-way state. You understanding?
Yes.
Then X start state. Have you ever heard about these states?
Nope.
No.
So this is what happens over here. That's why it's a bit complicated protocol. So in its state, whenever you have to establish a neighbor relationship, R wants to have a R2 relationship. So the process is basically divided into 6 status. One is init state when a router sends, even if you're going to start from R2, same thing happens. I just took an example of R1. So it sends the routing packet. That means right now the R1 is in init state. Now when it reaches to R2, it receives and sends the hello message. That means it's two-way state. Now X start is beginning of the LS DB exchange between both. When both the routers will send the hello packets of each other, then it's the time to share the information. What is that? It's beginning, BIGNINNIG, beginning of the LSDB. What do you mean by LSDB? It is link state database exchange. First, I told you it's routing. Our routers in the routing network will share the entire network topology. So in the network topology, we have LSDB, which is link state database. So when it's going to start, when both the routers will share the hello packets, third stage will go, and the name of that state is X state. So it will start beginning of LSDB exchange between both routers, R1 and R2. Routers are starting to exchange link state information. So routers, at this stage, routers have started to exchange only link information, which is just the basic information, exchange link info or link state information, you can say. Fourth state is exchange state. What's exchange state? Now database, there is one more term, there is one more thing which is in the network topology, which is DBD, and it stands for database descriptor or descriptor. So at this stage, the DBD packets are exchanged. So these DBD packets contain basically what's the information in them? They contain LSAs headers or LSA headers. That's link state authentication headers. So routers will use this info or information to see what LSAs need to be exchanged. At the fifth step is loading state. What's loading state? One neighbor sends us now LSRs. So one NEIGH, let me write it. I will explain it to you using an example. So sends link state requests. So it's called as link state requests for every network it does not know about. It does not know about. The other NEIGHBOR neighbor replies with the LSUs, which is link state updates. Which contains information about requested networks. So after all the requested information have been received, other neighbors goes through the same process, and at sixth time we have another state called full state. Both routers have the synchronized database and are fully adjacent with each other. So in the full state, all the routers, or you can say we're using only two, so both routers are having the synchronized database, or you can say synchronized, not mized, it's nized database, and are fully adjacent. Now adjacent with each other. Adjacent means they are having the same routing topology. So let's explain, and let's try to another time. I'm gonna go here instead of checking it here. Now I'm gonna draw the same two networks here. Suppose this is my R1 network and this is my R2. Try to understand. So suppose there are two subnets here. We have also two subnets. These are three directly connected. So it has he. So before they're having the routing information of all these networks, so we have to establish a neighbor relationship. So how we have to establish a neighbor relationship? By sending the hello packet, right? Let's talk about this R1 router. So from this side, it's the demonstration. So from this side, when this R1 will send a hello message to this particular R2, It's a simple thing. It's right now this R1 and R2 both are in its state, or this R1 is in its state. So a router has sent a hello message from the other OSPF router. You understand? Or from the other OS that's in its state. So that is when you send the hello packet in order to establish a neighbor relationship. Second state is two-way state. Two-way state is the neighbor, now this R2 has received the hello message and replied with a hello message of his own. So when you send a packet and then he sent you a packet back, or she sent you a packet, the router sent a packet back. So that is you are in now in two-way state. So you have started, now you can go ahead. It's simple. When you come to meet me, you will first of all come, right? So you are coming, I'm also coming to meet you. We take a central point. So that means when you come, we are in init state. When we come, we shake hands. That's two-way. We shake hands. When we shake hands, the next thing is X start state. What's that X start? Beginning of the LSDB exchange. At that time, we are saying that, how are you? All good. Where was you? I was looking for you for a long time. These are the things that we do. And the same thing happens over here. X start beginning or X start state is basically beginning of LSDB exchange. So it is just going to start receiving or sending. So this R1 will start sending the link state database. Both routers will start. So router have started to exchange just the basic information. What is there in the routers? Second is exchange state. In this particular exchange state, as the name implies, as the word said, as the word says, exchange state. It's DBD, which is database descriptor packets are exchanged. So database description packets are basically exchanged between the two routers. So they contain basically LSAs. It's link state advertisement, I guess. Yeah, it's link state advertisement headers are exchanged. So routers will use this information to see what LSAs need to be exchanged. So as I've told you, when a router shares the database, it's not going to take all, it cannot take, you are just, you just came to me, I told you I need some notes. And now when you come to me, you will give me the notes, you will be having a bundle of notes with you, but I will just fetch. That's what exchange state is. I will just see, I will just check first of all. So I do have this notes, I don't need this. Then I will check, yes, this particular note I need this particular paper. So I will just fetch, if it's a 100-page notebook, I will just fetch, yeah, I need this, but I do not need all the 100 pages of that particular notebook, of that notes. So in this state, these things are going to happen. So it will just check what LSAs need to be exchanged. So what already this particular router is having, it will not take them. So whatever is new in this R2, it will just take those, not all. Are you understanding?
Yes.
Loading state after that, the fifth one neighbor sends now link state requests for every network it does not know. After that, when it loads, so next thing is your neighbor will send LSRs, which is called as link state requests to every network which he's not having information of. For example, now he wants to gather information from other neighboring routers, so it sends LSRs for every network because now this R1 is having only information about this, so it sends the information or just LSRs to the other neighboring routers. The other neighbor replies with LSU. So when it sends the link or when it sends any information or packets, those are called as LSRs to the neighboring routers, which he's not having the information about. So those neighboring routers will share link state updates, which contains information about requested networks. Suppose that now we have one more particular router here, it's connected to that. And after it receives the first one, then it will send LSRs, link state requests to this router, and these routers will share the information which this router is not having in the routing table. Now he does not know this particular router is having 2 more subnets. You understanding? But they are not inside this routing table of R1. So what they do? So LSR, this particular R1 will send LSRs, which is link state requests. It will send LSRs to this router. So this router will this router will just request them what is in your routing topology. They will share the routing topology. Again, the same thing will happen, exchange state. The router will check what are the things that I have in my routing table and what are the things I don't have. So if there are the things which are already there, it will just drop those things, but it will take those, like those two things, two subnets from this. And that's called as loading state. And then when all the routers will share the information to each other, and at last there is a full state, because every router will have the network topology inside their tables, inside their routers. So these are the 6 states of OSPF neighbors. So it has to go through, always whenever you talk about hello packets, they are whenever you create a network of OSPF, they are going through 6 states. Init state, when router sends the hello packet; two-way, when router sends, another neighboring router sends the hello message back to the router; exchange state, where they're going to start some basic database information; then exchange state, database descriptor is just exchanged; and then load state, where it's going to just send LSRs and LSUs will be updated; and then full state. So this is the entire information about these 6 status. Okay, clear?
Okay.
Yeah.
Yes.
Now after it, these were OSPF status, OSPF areas. Now, as I told you, here it's nothing like autonomous systems. It's about OSPF. Autonomous system is still there, but area is very important. So OSPF uses the concept of areas, not of autonomous systems. So an area is basically a logical grouping of contiguous contiguous networks and routers. It's basically logical, making logical areas, not like physically I have this particular room, it's my area, there's a lobby. But here we are basically making this same thing, but based on logic. Not like we have routers, it becomes, so we cannot physically say that I will put 3 routers I will put in this particular room and 3 routers I will put in that particular room. No, even logically, we are creating areas, the same thing, like we have area, for example, this is our dining area, this is our bedroom, and this is our washroom, and these are areas that we create, but we create them physically. But in OSPF, we create areas logically. And there is an area ID that we are going to give to each router, which should be having the same area ID. All right. So all routers in the same area have the same. So all routers in the same area have the same topology table, but they do not know about routers in other areas. So the main benefits of creating areas is that the size of the topology and routing table on a router is reduced. Why we are creating areas first? Because as I've told you, distance link state vector routing protocols, link state routing protocols share the entire network topology. So it becomes very difficult for us to share the entire network topology to all the routers within a network. If it's like a network of 50 routers, at that time it will be a very difficult process that one router will share the network topology other than other. It will increase the bandwidth, it will use more bandwidth, and convergence will be very slow. It will not be faster like AIGRP is having. Are you understanding? So that's why they have given a concept. Okay, OSPF is giving us or sharing every time, after every 5 seconds is giving hello packets, and it's going to share the entire network topology. So what we will do is we will just divide it into a logical area, so that in that area only we will just have to, even you are in the same network, you have 10 routers, we will create area of 5 routers separate and area of 5 routers separate. So this is the concept. All right. So
Okay.
every area should be having a unique particular, you can say, area ID. So which I'm going to tell you here now. Suppose that we have one network here. This is one router, another router, and this is another here. And another, we have one router here, one router here. So this is one area, 1 and 2, and this is another area. This is 0 area, and this is 1. So this is one area. This is how it's logical bending of networks. This is another. So this is area 0, A0, A1. It's having everywhere OSPF enabled, but this is different network and this is different network, which you're going to understand. This is what is the concept of areas. So when you configure OSPF here, this should be having the same area, this should be having the same area, this should be having area 1, this should be having area 1, this should be having 0, this should be having 0. And this is called as border, or you can say area border router, ABR. We have two things in here, ABR and also a router which is going to link you to other particular network which will be having any other protocol implemented, ASBR. So OSPF areas, they are having two things, ABR, which is area border router. So this area border router is a router which will help you to link or to transmit the data of one area with another. And that router is called as ABR. So the router which we are basically using to transmit the data of areas together, to connect two areas together, 0 and 1 or 1 or 2 or 3 to 4 together, that's called as ABR. But now if we have another network here and it's using EIGRP and it's having different subnets here. So when you communicate, when you try to just connect this entire network with that particular network over here, which is implemented using EIGRP, at that time, the router that we're using, it's a central router, and this router is called as ASBR. What do you mean by ASBR? It's Autonomous System Border Router. You understanding?
Yes.
So within a network, we are using ABR, which is area border router. So if we have 5 routers, we can put them under one particular area ID. We have another 5 routers, we can put them in another area ID like 1. And if they have to get connected, we are using one central router, and that router is called as ABR. You understanding? And now if that entire 10 net routers are about to, suppose that we have now another building where we have implemented, another particular office or branch, or you can say even OSPF, so or even any other particular campus and near to this particular network. So we have implemented EIGRP over there. So the router that we are using to connect to that particular network, which is configured by EIGRP, which is here, that router is called as ASBR, which is Autonomous System Border Router, ASBR. Clear with this concept?
Yes.
So you will get more clarity when we'll go to the configuration part. So that's the main problem why we create areas. The main benefit of creating areas is the size of the topology, because we cannot share routing topology on the entire 10, 20 routers. So the routing table on a router is reduced, less time is required to run the SPF algorithm, and routing updates are also reduced. That's the main important concept why areas are being implemented in OSPF, just because to reduce the routing table, to reduce the work of SPF algorithm, and also to reduce the work of routing updates. So when we establish these things, so as I've told you, each area in the OSPF, each area, as I've told you, each area in the OSPF network, every area in the has to connect to the backbone area, which is mostly always area 0. We have area 0 by default. So one area should be, you have to give one area 0, which is very mandatory. Then whatever the areas you're going to connect, and they have to connect to that backbone area always. So each area in the OSPF network, suppose that this is the area 0 network, so all these other areas, like we have 3 here, 4 here, so they have to connect to the backbone area. This is first thing, okay?
Okay.
Second rule is all the router or routers inside an area must be having the same area ID to become neighbors. OSPF NEIGHBORS. So now here, what do you mean by this? Now, this is basically now one area, and now we do not have to establish neighbor relationship with the other area, which is 1. But we have to establish neighbor relationship with these 3 routers only, or even if there are 3, 4, 5 routers. So they are all in same area ID, like area ID is 0, which is the backbone routers, or which is the backbone area. So they have to establish neighbor relationship. So to establish the neighbor relationship between the areas, all the area ID should be same on all these 3 routers or 4 routers. Okay? There are 2 only. So that is another thing. And then only OSPF neighbor relationships will start. So a router that has interfaces is more than one area, or as I've told you, a router which is going to have interfaces in more than one area. Suppose the area 0 and area 1. For example, it's called as area border router. As I've told you, I just told you in simple ways that when one area will be connected to another, we're using a router called ABR. But you can say that if a router is having interfaces connected to more than one area, which is, for example, 0 area and 1 area, so that is called as ABR router. You understanding?
Yes.
So a router that has interfaces means ports, interfaces in more than one area, like area 0 and area 1, is called as ABR, area border router. And now a router that connects an OSPF, so a router that connects an OSPF network, the entire OSPF network, to other routing domain. For example, EIGRP network, as I've told you, for example, just not for example, just say network that's called as is called ASBR, and it stands for, as I've told you, autonomous system border router. So a router which is having interfaces in more than one area is called as ABR. A router which connects the entire OSPF network, which is here, this entire network, to another routing domain like EIGRP, this router is called as ASBR. And this point you have to note, it's very important. As I have told you, there's a major difference in manual route summarization in between OSPF and EIGRP. In EIGRP, I told you manual route summarization can be implemented on any interface of a router, right?
Yes.
But in OSPF, it's not like that. In OSPF, manual route summarization is possible only on ABRs and ASBRs. So this point is very, very important. So in EIGRP, we used to have the manual route summarization. We can do it on any particular interface, but in OSPF, we can go through the manual route summarization only on ABRs, this one router, and ASBRs, okay? Which will help us to connect two areas and two different networks together, okay? Clear?
Okay.
So this was the
Yes.
concept of, OSPF. These are the things which you have to remember always. And there are some one or two things more, and then we'll start the implementation phase, or you can say OSPF configuration, and that we are going to start. I'm going to talk about, I told you about LSA, what LSA is again, to make you understand, then LSU and LSRs. And we'll move ahead with the configuration. So in the next class, we're going to start configuration part of it, and make sure that you're going to just repeat these things and try to remember what I have taught you. Okay?
Okay.
Clear?
Okay.
All right, I'll see you tomorrow, and I hope, yep. Wait a sec, let me check whether I have, yep. Attendance is done. Who was present today?
All except Hadil and Tahani.
Sahani was not here, okay. All right, so see you guys on Monday at same time, inshallah. I was, yeah, you have goodbye. Take care of yourself and stay safe, okay? And work hard in this Tectrons and get the best results. Bye-bye.
Inshallah.
Okay, bye.
Bye. Take care.